Yeah, thanks very much to the organizers for inviting me. This was a little bit of a last-minute trip, but it's been wonderful being here. So today I want to tell you about some recent work on analyzing and observing phases of quantum dynamics, which are really induced by quantum measurements. So this is building on theoretical work done in collaboration with Matteo Ippoliti and Tibor Rakowski, and an experimental collaboration with the Google team, which was also co-led by Matteo. Okay. So in this conference, we've heard many talks. As we've heard in many talks in this conference already, over the last decade or so, there have been many interesting developments on understanding universal phenomena in the dynamics of many-body quantum systems, largely motivated by breakthroughs in experimental capabilities for studying well-isolated quantum systems and for studying these in settings that are far from equilibrium. So, we've made a lot of progress in our understanding of thermalization, quantum chaos, scars, many-body localization-driven phases, dynamical freezing, and so on. But by and large, most of this work, so by and large, this body of work has focused on the unitary dynamics of well-isolated quantum systems. However, if you open a standard quantum mechanics textbook, unitary dynamics is only one half of the story, right? One of the biggest, so usually we think of quantum states and they evolve according to Schrödinger's equation, except when you make a measurement, right? And the unsolved measurement problem in quantum mechanics is that these two sets of rules have very, very different effects on the quantum many-body state, right? So Schrödinger's equation evolves the state according to a linear, smooth, deterministic evolution, while measurements are nonlinear, discontinuous, random. They cause wave function collapse. So when you make a measurement, you get some particular outcome, and the outcome that you get is inherently stochastic, it's random, and you get a particular outcome with a particular probability that's given by Born's rule, right? And usually in physics or in condensed matter physics, we spent a lot of time focusing on what happens to systems under unitary time evolution, but measurements have been viewed more as a probe of the correlations that exist in the system, right? So for instance, in condensed matter physics, if someone hands you a state of interest and you want to deduce something about the correlation functions that exist in the state, well, then you make many measurements on some device, and using those, you deduce some expectation value for that correlation, okay? But again, measurements have this dramatic effect on the state being measured. So instead of just being used as probes for existing correlations, measurements, in fact, can create and restructure and destroy quantum correlations on their own accord. Okay, so the talk that I'll be presenting today falls under this topic called monitored dynamics, which have gained a lot of interest over the last 3 or 4 years. And the general philosophy in studying monitored dynamics is to elevate the role of measurements from passive probes to active components or protagonists of many-body dynamics. Okay, so measurements are going to enter the dynamics in their own right, and they're going to be used to create, restructure, destroy quantum correlations in their own right. And then we're going to ask about universal phenomena that we get with measurements playing an active role. Okay. And of course, just like much of the work on unitary dynamics was motivated by experimental advances in building coherent quantum simulators, measurements are also very much a part of the capability of this new generation of quantum devices, because the operation of a quantum computer, which is some late-time goal, which we may or may not never ever get to, the operation of this quantum computer is inherently a monitored, interactive, out of equilibrium quantum process. Right? So if you're operating some kind of quantum device, you have in mind that you're going to be acting with unitary gates, you're going to be making measurements, maybe you can process those measurement outcomes in some classical computer. Based on what you process, you might feed those, you might determine what you do next. But this whole sequence is inherently part of the operation of any kind of error correction sequence or any kind of quantum algorithm, right? But this has in it all of these different ingredients that I was talking about, which is a drive to create these unitary gates, to act with these unitary gates. Controlled measurements, okay, so there's the controlled measurements for output, readout, error detection. There's always noise in the system, which is uncontrolled measurements. You can think of noise as the environment making uncontrolled measurements on your system. And then feedback, for instance, error correction, which is you process these measurement outcomes and you do something. Okay, so the question is, what new universal phenomena can we get if we combine all of these different out of equilibrium ingredients, and in particular, placing a central role on controlled measurements? Okay. So to set the stage for why this could be something very interesting, let me just spend a few slides talking about the remarkable effects that you can get in terms of creating quantum correlations when you put measurements into the mix of what you're allowed to do. Okay, so this is probably this is a standard example from any quantum information textbook, right? Which tells you how you can use a controlled measurement to teleport a quantum state. Okay, so when we're thinking about quantum dynamics, we're usually talking about some arrow of time, but that's always defined under unitary time evolution. Okay, so there's a conserved flow of information from the past to the future, which defines this arrow of time. But with measurements, this arrow of time actually loses its special meaning and becomes interchangeable with spatial dimensions. Okay, so quantum teleportation is one example of this, where you can transmit some state across some widely space-like separated interval by making a controlled measurement. So in the standard protocol, there's some shared entanglement, some EPR pair between Alice's lab and Bob's lab, and these could be very, very distant from each other. Alice has the state that she wants to send to Bob, and to do that, she makes this joint measurement, an EPR, a Bell measurement on her qubit and a qubit from Bob's lab. She calls him up, so this is the classical communication part, okay? She calls him up, tells him the result she got. Based on this result, he does a little operation on his qubit and out pops Alice's state, okay? Even if she didn't call up Bob and tell him this measurement outcome, 1/4 of the time, when you make a Bell measurement, you can get four possible outcomes. 1/4 of the time, Bob would have had to do nothing and the state would have been transmitted from Alice to Bob, okay? So this is an example of creating correlations across widely separated intervals. This is even more transparent with this little cartoon here, okay? So what's being done here is at time 0, you can prepare a whole series of Bell pairs, okay? So there's no long range entanglement. Ignore the red portion for a moment. This was supposed to build, but it didn't. So I just have a whole bunch of Bell pairs here. Okay, so this you can create with a local circuit, because these Bell pairs are totally disconnected from each other. And then you go in and you make these joint measurements on these Bell pairs. Those are the reds. Okay, and let's say you post-select on getting a particular EPR pair when you make these measurements. When you've done that, after making these measurements, so we did one round of unitary gates to create these Bell pairs and one round of measurements, you've actually created entanglement between this qubit and this qubit very, very far away, just with one round of measurements and one round of unitary gates, okay? And this can be arbitrarily distant, okay? And you can really think of this as this is in space, but you've created this entangled connection between these two qubits in space by making these measurements. Yep. Yes, so these are these two qubits at a time that are being measured. So I'm just measuring 2 nearby qubits at a time. So first I entangle 2 nearby qubits at a time, and then I measure 2 nearby qubits at a time. So I'm not doing anything non-local, but by doing this 2-step local process, I can entangle arbitrarily distant qubits. Yeah? And this, in a way, goes against the usual lore from condensed matter physics, where we say that 2 phases. This is where we think the 2 gapped phases belong to 2 separate phases if there isn't a finite depth unitary circuit that can take you between them, right, without closing. So sorry, I garbled that up a little bit. So when we think about phases in condensed matter physics, if you have gap phases, we say that all points that are adiabatically connected to some point in this phase belongs to, some point here belongs to the same phase. And indeed, you can go between any 2 points in the same phase with a finite depth unitary circuit, okay? But if you want to go between points in different phases, then you need a circuit depth which scales with the volume of the system. That's the usual law. But when you have a circuit that includes measurements in it, you can go between these gapped phases just with a finite depth circuit of unitaries and measurements. Measurements are very powerful. This is another illustration of how you can create long-range correlations that may characterize some phase here by the act of making measurements, okay? So one example of this, which we don't have to dwell on is, if you want to prepare a toric code ground state, one way to do that is to start with a simple product state, measure these 4-body star operators, which are the toric code stabilizers. Where these operators flag and give you -1 tells you where the anyons in your system are. And then you can actually pair up these anyons with just a depth 1 circuit, and you're left with the toric code state. Okay, so we know that the toric code is topologically ordered. If you wanted to use a unitary circuit to prepare it, that circuit would have a depth that scales with the system size. With measurements, you can do this in depth order 1. Okay, so this is another illustration of how measurements are very powerful. So what I want to talk about are dynamical phases of measurements. So we want to think of measurements as a part of these many-body dynamics, and I want to ask about what kinds of interesting non-equilibrium phases can you obtain by putting measurements into the mix, okay? And, again, the lore is that if you're talking about quantum dynamics, the usual outcome is thermalization to some thermal state. And if you're at some high temperature, if temperature doesn't even mean anything, if you're talking about a Floquet system, then that's just a boring outcome, unless you rely on something like many-body localization or quantum scarring or dynamical freezing to prevent that equilibration to that boring state, okay? So here, measurements are going to play the role of the thing that sucks out entropy and prevents you from thermalizing to a boring state. And measurements are going to simultaneously prevent that thermalization to the boring state and be used to create interesting correlations, okay? And one important point here is that when we're thinking about these non-equilibrium measurement-induced phases, these are going to be defined by the structure of quantum information in space-time, okay? Because as I said, with measurements, space and time individually are not very meaningful. They can be interchanged into one another. So even when we characterize these phases, we're going to be thinking about the structure of quantum information in space-time. Okay, so there's been a lot of work on thinking about different types of phases in monitor dynamics with lots of additional structures. But for this talk, I just want to focus on a minimal model and a minimal phase transition. So a paradigmatic model is that of a random unitary circuit. So each of these are unitary gates, which are drawn randomly from some ensemble, and they're interrupted with local single-site measurements that are made with some probability p. Okay? So each time you run this evolution of random gates and single-site measurements, you get a particular quantum trajectory out with some probability, which is determined by this history of measurement outcomes. So on net, this gives you this ensemble of trajectories, psi m, with their individual probabilities. And you get this, and this measurement-induced phase transition, this minimal version of it, is a phase transition in the ensemble and the structure of these trajectories, for instance, as you tune a parameter like the measurement rate. Okay, so you can tune the probability by which you're making measurements in your system, and as you tune that, you get this measurement-induced phase transition. So what are some signatures of this transition? One intuitive picture to have in mind, and a lot of different diagnostics that have been proposed kind of fit into this, is that as you're running these dynamics, there's a web of quantum information, a web defined by spatiotemporal correlations in space-time, okay? And this quantum dynamics builds these connections. Measurements can simultaneously sever the connections or rearrange them. And the question you want to ask is, as you're making these measurements, does this web remain connected or does it break up, okay? You can imagine that if you just make measurements everywhere in the system, everything gets disentangled, there are no long-range correlations. So you want to ask, does this web of connections, is it robust to the presence of measurements? Now, there are various diagnostics of that. The first is, and this was the first one that was proposed, is entanglement in some late time state. So now I'm thinking of time as you would do in an experiment when you actually run the experiment. You run these dynamics, you're left with the state at the end, and you ask, is that state at the end area law entangled or volume law entangled? If it's volume law entangled, that means that there's a lot of, that means that this web is tightly connected, and if it's area law entangled, that means the web is loose or sparse. Okay? Another manifestation of this transition is in the teleportation properties of this circuit. Once again, you run these dynamics, you make these measurements, and you ask, if you had purely unitary dynamics, then you would have a light cone, and the light cone tells you whether distant parts of your system can be correlated or not. So for instance, if I had purely unitary dynamics, this region here denoted by the red bracket and this one denoted by the blue bracket, these are causally disconnected and there can be no correlations between them. But just like in the teleportation example, when you have these measurements and you're building up this shared structure, these measurements can induce correlations between these causally disconnected subsystems. And that itself, that is also a manifestation of whether this web of quantum information in your system is tightly connected or broken up. Okay? One point that I want to emphasize here is that when we're talking about this transition, this is a transition in individual quantum trajectories. Okay, so I prepared this late time state and I asked about its entanglement properties. And again, as I said, each run returns this one state to you. And this entanglement phase transition tells you that as you tune the measurement rate in your system and you look at the quantum entanglement properties of psi1, then for a small enough measurement rate, you're in an entangling phase or a volume law phase, whereas as you tune the measurement rate up, this becomes disentangled and you get an area law. Okay? So this is the entanglement properties of the individual quantum trajectory. And the reason that this transition is initially, the existence of this transition is somewhat counterintuitive or surprising is that, you're making the disentangling phase is easy to understand, right? You made measurements everywhere, you get an area law phase. There's nothing surprising there. But think about the volume law phase. As you're running this circuit, if you take some region in your state, correlations can only build up, entanglement can only build up at the boundaries of that region. But you're making measurements everywhere in the bulk, okay? So naively, bulk measurements, which are disentangling your state, cannot compete with a boundary generation of entanglement. So you might have expected that at any non-zero measurement rate, you would have ended up with an area law phase. Okay, and indeed, when this set of papers first came up, this was a matter of some debate as to how this volume law phase was even stable to this finite density of measurements. And that stability is actually hidden in these in a particular structure of entanglement in this volume law state. It's not just a thermal volume law state. It's a particular kind of non-thermal volume law state with a particular kind of arrangement of entanglement correlations that allows this resistance to measurements. And signatures of that can be seen in these kinds of universal subleading corrections that show up to the leading volume law piece. Okay, so I won't have time to talk about that, but we spent some time thinking about those. Yeah. Yeah. Yes. Yes. Yeah, that's right. Yeah. Yeah. Yes. Correct. That's a product state. That's right. Yeah. Yeah. The bath is a different story. So okay. So that's good. So that's right. But that isn't, when you have a bath, that's averaging over all the quantum trajectories. So the difference between monitored dynamics and dissipative dynamics is in a monitored dynamics, you have a notebook. That's the monitoring part. You're writing down every measurement outcome and following these individual trajectories. Whereas in a dissipative dynamics, you're just tracing over all of them and you get a mixed state density. And if you trace over that, and that'll come to soon, I'm going slower than I expected, then you just get something trivial and you don't see anything. It just looks volume. Okay. All right. So there's various different information theoretic manifestations of this transition. And this thing that I was just telling you, that it's somewhat surprising that you can encode your quantum information, that you can have this entanglement that's resistant to measurements. And this perspective on this transition has been formulated in terms of the emergence of a dynamically generated coding phase where local measurements aren't able to learn about the system. And that gives you this volume law, as opposed to the area law phase where measurements gain a lot of information about your system and destroy that entanglement and that correlation. Okay? So there's lots of these interesting perspectives all describing the same transition. But again, intuitively, all of these are describing either a tightly connected web of quantum information in space-time, or a disconnected web and a transition between these through this measurement rate. Okay? So what about experiments? Soon after the theoretical proposals, there were two experiments on superconducting qubit and trapped ion systems, which basically followed, which did exactly this. That there was a random circuit, measurements were interspersed in it. And now, because of this need to follow individual trajectories, which I'll come to in a minute, these experiments really weren't scalable. They suffered from a post-selection problem that I'll mention in a moment. But they were very nice demonstrations of the underlying physics, but on a small system, right? So what were the experimental challenges? One, in this particular way of doing things, you're making mid-circuit measurements. And mid-circuit measurements are costly on superconducting hardware. They cost roughly 10 times the gate time. Second, there's environmental noise that Arnab just talked about, which is that the system is getting entangled with an environment. You can't get around from this. And if it's getting entangled with an environment, it's always going to give you a trivial volume law rather than this more structured volume law. And third, you need many, many shots to measure the entanglement. If I give you some particular state and you want to measure its entanglement on a quantum simulator, you need to prepare that same state many, 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 many times. But the randomness of measurement outcomes leads to this fundamental post-selection barrier in your ability to do this. This is not a problem about quantum control or just making your experiment better. This is a fundamental limitation from the rules of quantum mechanics. Okay? So to elaborate on this just a minute, again, what we're talking about is a transition in a given trajectory. So you start with some wave function, you're doing unitary evolution. Each time you make a measurement, you can get two possible outcomes, which defines two different branches in this wave function. And each time you do this, the number of branches keeps growing. It grows exponentially with the number of measurements that you've made, or with the space-time volume if you're making measurements at some finite rate. So if you want to know about the properties of this one particular trajectory characterized by this one sequence of measurement outcomes, you need to prepare this same trajectory many, 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 many times. And doing that just means that you're paying this exponential cost, okay? And this is really important, again, because if I average over all of these trajectories, which is what you would do if you just had a bath, then you would get this trivial equilibrium density matrix, and there would be no signatures of this transition. Okay, so this is just saying this. Okay, let me say one more point about this post-selection problem. Okay, so we have to repeat this many times. This also means that when you're looking at the properties of your individual trajectories, you want to measure non-linear observables in those trajectories. Okay, because suppose you measured some linear observable, just like an expectation value of some operator in some particular trajectory, and then you averaged over all trajectories, that's the same as averaging this density matrix and measuring this operator in that density matrix, but that's just going to give you something trivial and you're going to get zero. Okay? On the other hand, if you measure something like entanglement entropy, then that's a nonlinear observable of your density matrix, and that survives. So you compute this in each trajectory, and then you average over trajectories, and that quantity continues to show you a signature. Okay? So measuring these, again, requires preparing multiple copies of the same wave function. So what did we do? So we came up with various different ideas, conceptual ideas, then implemented in experiments to try to overcome these three different barriers that I just presented in trying to do a large-scale demonstration of this phase transition. So what are the three takeaways from this talk? The first is that space and time are interchangeable in the presence of post-selected measurements. So we were able to use a variety of space-time duality mappings that moved measurements to the final time and removed the need to make mid-circuit measurements throughout the circuit. Okay, so this was not a fundamental barrier; it was an experimental challenge, but it still helped a lot with the kind of coherence times that were available to us. And in some cases, it also improves the post-selection barrier because you're only making measurements at the final step. Okay? The second is uncontrolled environmental dissipation. There's no way to completely get around that, but we actually came up with an order parameter that uses noise as a feature rather than a bug, because these two different phases that we're talking about actually have very different responses to noise and how they respond to noise. So we were able to use noise and the different responses of these phases to noise to diagnose the transition. And finally, the most fundamental barrier that we have, which is unique to the measurement-induced phase transition, is this post-selection problem. And in order to do that, we formulated a hybrid quantum classical order parameter similar to this cross-entropy benchmark order parameter that was there in Google's first quantum advantage experiment, if you're familiar with that. And this quantum classical order parameter allowed us to completely get around the post-selection problem at the cost of classical simulation. Okay, so similar to the cross-entropy benchmark, I'll come to this in a moment, you can replace this post-selection cost with the cost of classical simulation. Now, of course, there's no free lunch. This isn't perfect, but it still allowed us to go from a system of about 10 qubits to a system of 70 qubits. And this is basically as large as any other quantum simulation that exists to date, despite the presence of this barrier. Okay. So let me talk about each of these three in turn now. So first, if you're talking about space-time duality, okay, so as I said, unitary dynamics is defining this arrow of time, and conditioning on measurement outcomes breaks this. So this gives you a flexibility in redefining space and time. So if I have the standard setup of a monitored evolution, you start out at time 0 with some qubits, you're acting with unitary gates, you're making measurements, and you get some output state, and you want to know the entanglement properties of its output state. Okay? There's a different way of thinking about this problem, which we formulated here, in which you're running unitary evolution, you're starting with some input state, you're running unitary evolution everywhere in the bulk, you're making measurements at the final time slice. So think of this as a tensor network, and then you have this set of qubits that live on this time-like slice in your circuit, and this set of qubits acts as if it had undergone monitored evolution, okay? And the way you should think of this is you're actually contracting the circuit space-wise, okay? So you can imagine that your input state actually lived in this slice, in this time-like slice, and then your space is like doing a monitored evolution. You're running this circuit sideways, and if you take a unitary gate and you look at it on its side, it actually ends up looking like a monitored post-selected gate. Okay, so by running this circuit sideways, you end up with an evolution that looks effectively monitored. So this was very powerful. It helps us, we started by doing this experiment. It's not completely general because not every type of monitored evolution can be implemented in this way, but a large class can, and it still teaches you interesting things by varying the classes of unitary gates that you use in this ensemble. To make it more general, you can look at a 2D circuit, okay? So now you have a 2D shallow depth circuit, and you're doing unitary evolution and then making measurements at the final step, leaving one row of unmeasured qubits. Okay, so this is a standard experiment that these various platforms can do very easily because you're starting with this 2D chip, you're doing unitary evolution, and then you're making measurements at the very final step. This is what any experiment will do, right? But then this final layer of unmeasured qubits that you have, this output state, this you can figure out exactly the type of way in which you can map this evolution to an effective monitored dynamics of an effectively one-dimensional system. And again, the way to think of it is to think of a 1D system undergoing some space-like contraction, which is making it look monitored. Okay, so what this gives you is a finite, the entanglement transition maps to a transition as a function of depth in this two-dimensional circuit. So you're again taking this output state and you're viewing it as a state that has undergone monitored evolution. And roughly the number of gates in this circuit is Lx times Ly times time, whereas the number of measurements is only Lx times Ly, which is right at the end. So the measurement density is inversely proportional to the circuit depth. Okay, so you can make this more precise, but roughly as you scale this circuit depth, you end up undergoing a transition in the entanglement properties of this output state, where it goes from being, again, volume law entangled to area law entangled, and the circuit depth plays a role of an effective measurement density. Okay? And Aram Harrow used this mapping to actually also show how this can be related to a phase transition in the complexity of simulating finite depth quantum circuits, which is another topic of much interest, because of course, if you make the depth very large and your system is volume law entangled for this effective chain, then you can imagine that might be harder to simulate than if the system is area law entangled. Okay? So we started by doing a brute force calculation of this finite depth transition, where we had these layers of 2D evolutions. We made measurements. We were left with an output state. Because now we're going to explicitly do post-selection, we were limited to 12 post-selected bulk qubits and 7 qubits on the edge there. Okay, and then we measured its entanglement properties as a function of depth. And this is the volume of some subsystem in region 8, only goes to 7 sites. And you can see that, you know, for large depth, something looks volume law-like. It's at least growing with subsystem size, whereas for small depth, there isn't a strong dependence on subsystem size. But you know, this is kind of the best that you can, and we looked at some other measures, but this is the best that you can do with this small system, right? Like you can't really talk about volume law and area law very much with just 7 qubits. So in order to scale this up all the way to 70 qubits, and in order to finally resolve the transition, okay, if you're thinking of circuit depth, that's a discrete variable because your depth can be 1, 2, 3, 4, 5, but we want to get an actual transition. So we scaled this up to 70 qubits, we fixed the circuit depth, and then we decided to tune a different variable, which was the probability with which we were applying gates. Okay, now that's a continuous variable. So this gives us an effective depth, which is controlled by this parameter rho, and you can get a phase transition again as a function of rho, and this rho is tuned between 0 and 1. Okay, so if you apply these gates all the time, you're going to be in a volume law phase. If you skip out in them, you're going to be in the area law phase. Now we're going to go all the way to 70 qubits. But there are 2 problems here, right? I can scale up to 70 qubits and try to repeat the experiment, but I'm going to run out of steam very, very quickly for 2 reasons. First, I'm going to have to pay this post-selection cost. And if I'm going to do that naively, then I'm going to have to do that on nearly 70 qubits, and there's no way I can do that. Second is, I want to actually measure the entropy, right? To decide whether I'm area law or volume law, I have to measure the entropy of this output state. But measuring the entropy is itself an exponential measurement, which scales with the size of the subsystem. So if I have a large subsystem there, measuring that entropy is also going to be costly. So to get around these, we need a sample efficient probe of these phases. And we did this in 2 steps. The first is to get around this naive, okay, so sorry, do I have 5 minutes? Yeah, okay. So the first thing that we wanted to do was, instead of measuring the entropy of the whole system, we wanted to measure the entropy of just 1 probe qubit. So this builds on an idea by Gullens and Hughes. So you have your circuit evolution, you start making measurements, and you select a probe qubit, you run this evolution, and then you measure all these qubits at some radius r, okay, that's this decoding radius that's being measured, denoted here. And then you ask, is the probe qubit still entangled with the rest of the qubit, the rest of the system or not, okay? And this ends up being, there's a stat-mech understanding of this transition, so you can show that this will exactly diagnose the two phases. And again, intuitively, in the volume law phase, you have this dense network of quantum correlations, quantum information. So if you entangled this probe qubit and you made these measurements, it actually remains entangled. So now in this volume law phase, your probe is still entangled, but in the area law phase, everything breaks up, your connections break up, so this probe qubit gets disentangled. So as you're tuning it, you've now reduced your problem to measuring the entanglement of just one qubit. And that's great because measuring the entanglement of one qubit is very cheap. But we haven't yet gotten around the post-selection barrier because this is the entropy of one qubit conditioned on a measurement record. And that part is still costly, okay? So to get around that, we devised a hybrid order parameter, which uses data from both your quantum simulator and a classical simulation, okay? So the entanglement of a probe spin, you're just talking about one spin here, is characterized as quantified by the length of its block vector. So that's what you want to measure. But the problem is that every run of your circuit, okay, every measurement record gives you a block vector pointing in a different direction. So if you just averaged over all of these block vectors naively, you would get nothing, okay? And that's again, the need to prepare multiple copies so that you can average something like AM squared over the measurement record, some nonlinear observable. So the way we solve this problem is, when you run your experiment on your quantum chip, you get out an output state and a measurement record. Now you feed your measurement record to a classical computer, which can reproduce a simulated version of that state. And then you use that you cross-correlate the quantum data with your classical simulation to devise this kind of hybrid quantum classical order parameter. So essentially, you needed 2 copies of your state, but you're getting 1 copy from classical simulation. Okay? And this idea is not is really like a version of this idea was used even in the first Google experiment, because there they wanted to know the probability of getting a particular output state at the final time. But you're never going to get that same output state ever again if you keep running the experiment over and over. So that probability was computed classically of a particular bit string. That probability was computed on a classical computer, and that probability was then averaged over quantum runs. So this is very much a similar principle that we used in order to get around that post-selection problem. Okay, yeah. It's not so it's not unknown. So you have you're running your experiment. You know what gates you're running. No, so in your experiment, you get a particular measurement outcome. So you write it in your notebook. And then when you run your actual classical simulator, you do a projector onto the upstate if you're making a measurement rather than, and that's how you would do the experiment anyway. Right? So that's a simulated experiment in a classical computer, and then you do a cross correlation. Okay. So there's an interpretation of this in terms of decoding that I'll skip over. So the upshot is that when we do this experiment, we can look at the entanglement of this probe qubit with the rest of the system, and we see that as we tune the gate density, we get this crossing or this crossover between the probe qubit being disentangled at low gate densities and being entangled at larger ones, with an apparent transition around 0.9. But the location of this transition keeps drifting, and it's drifting despite having done some kind of poor man's error mitigation, where we know that something that should be 1 is perhaps less than 1 because of noise, so we correct for that. But even despite that, we see this drift, which is a signal of kind of instability to noise and failure of noise mitigation. Then the last slide that I'll present here is, we try to then use noise as a feature. Okay, so again, if you have this dense web of quantum information, and you're asking about the entanglement of this probe qubit, if you have noise in your system, the noise acts everywhere, okay? And that's going to reduce the entanglement, that's going to get entangled with this probe qubit everywhere. So in the entangling phase, this is a particular quantity that should be 1 in the absence of any noise, and its reduction from 1 is telling you the effect of noise. And the point is that in the entangling phase, this is reducing, the amount by which it reduces scales with system size, and it scales exponentially with system size. Whereas in the area law phase, that doesn't happen. It's only sensitive to noise within some finite correlation net. And in the StatMech picture, this noise actually acts like a symmetry breaking field. So the order parameter's response to noise is like probing the susceptibility of a magnet to a symmetry breaking field. Okay, so we can really see how these two phases are responding very differently. So instead of just treating noise as a bug, we're looking at it as a feature. Okay. So to summarize, monitor dynamics can show rich phase structure characterized by various information theoretic quantities like entanglement and teleportation. Measurements are very powerful, and I think there's still a lot to be done in understanding how to extend the mental furniture of quantum dynamics to incorporate measurements in their own right. And a lot of work has been done on this already, but also much remains to be done in moving from random models towards more structured evolutions, incorporating symmetry and topology, and phases that are characterized by the flow and organization of correlations in space-time. And I just want to flag that Floquet codes, which are recently generating a lot of interest in the quantum information community, are one example of this kind of monitored evolution.
A little bit late, like a couple of questions.
Does it remains magnitude 1, or would it change because it's in the environment?
So the magnitude is going to tell you what the entanglement of the probe qubit is. If the magnitude is 1, then it's not in then.
So it's area law then, kind of. No, because you are also using noise to separate the phases.
Right. Okay, good. So that was I had to skip over that part. The point is that if you measure out everything, okay, then you're just left with the probe qubit. And if you were doing a pure state, if you're doing pure evolution and then doing measurements at the end and not tracing other measurement outcomes, then your probe qubit has to be disentangled. So then its block vector has to be 1, right? But if you see a reduction from 1 when you've measured everything out, then that means that it got entangled with the environment instead. So that's the reduction that I'm talking about, once you measured out everything.
So one quick question. So you said that the transition is from volume law to area law. What happens exactly at the critical point?
It's a log.
Is it
it's a log law.
Oh, I see. Okay.
Yeah.
Thanks.
Yeah.
I think we have to move on. Thank you very much again.